The birth of quantum physics traces its origins back to the 19th century, during a time when classical physics ruled the understanding of the natural world. Classical theories, such as Newtonian mechanics and Maxwell's equations, had provided an almost complete explanation for a wide range of phenomena. However, there were certain puzzles that these theories could not explain, one of the most significant being the problem of blackbody radiation. In simple terms, blackbody radiation refers to the electromagnetic radiation emitted by a body that absorbs all incident light without reflecting any. Blackbodies are idealized objects, often represented as perfect absorbers and emitters of radiation. The study of blackbody radiation became a central issue in physics because it posed a direct challenge to the classical theories of heat and light. At the time, classical physics, as governed by the laws of thermodynamics and electromagnetism, predicted that an object heated to a high temperature would emit radiation across the entire electromagnetic spectrum. According to Rayleigh-Jean's law, which was derived from classical principles, the amount of radiation emitted by a blackbody at a certain wavelength should increase exponentially at shorter wavelengths, especially in the ultraviolet part of the spectrum. This prediction suggested that, as the wavelength of radiation decreased, the intensity would become infinite, a result that was clearly absurd and contrary to experimental observation. This discrepancy was known as the ultraviolet catastrophe. In reality, experimental measurements showed that blackbody radiation followed a very different pattern. The radiation intensity increased with temperature, but began to drop after a certain wavelength, especially in the ultraviolet range. Classical physics was unable to account for this observed behavior. The failure of classical physics to explain the nature of blackbody radiation became one of the biggest unsolved problems in the field. Enter Max Planck, a German theoretical physicist, who in 1900 was tasked with resolving this puzzle. Planck was deeply invested in finding a solution to the problem of blackbody radiation. His approach would prove to be revolutionary, changing the course of physics forever. His solution began by questioning the very nature of energy itself. Planck proposed that energy was not emitted or absorbed continuously, as had been assumed by classical physics, but rather in discrete packets. These packets of energy were termed quanta, and the fundamental unit of energy was directly related to the frequency of the radiation. Planck's radical idea was that the energy of electromagnetic waves was quantized, meaning that the energy could only take specific values. He introduced the concept of a fundamental constant, now known as Planck's constant, denoted as H, which linked the energy of a quantum of radiation to the frequency of the electromagnetic wave. Planck's formula for blackbody radiation, known as Planck's law, successfully explained the observed radiation spectrum, resolving the ultraviolet catastrophe. Planck's law states that the intensity of radiation emitted by a blackbody is directly proportional to the frequency of the radiation and inversely proportional to the temperature of the object. The formula is written as follows: E equal to h, nu, where E is the energy of the radiation, h is Planck's constant, and nu is the frequency of the radiation. The introduction of the quantization of energy was a profound shift in thinking. Before Planck's work, energy was considered a continuous quantity that could be subdivided infinitely. Planck's hypothesis, however, implied that energy could only be transferred in specific discrete amounts. Planck's quantization idea was revolutionary because it contradicted the prevailing classical ideas of energy and light. The classical wave theory of light, championed by figures like Thomas Young and James Clerk Maxwell, treated light as a continuous wave. Planck's theory suggested that light, along with other forms of energy, behaved as both a wave and a particle. This dual nature of light would later become a cornerstone of quantum mechanics. The implications of Planck's work extended beyond just blackbody radiation. The concept of quantization would go on to play a key role in understanding atomic and molecular behavior, which had remained largely mysterious at the time. The idea that energy levels within atoms and molecules could only exist in certain specific values led to the development of new models for atomic structure, which would be further refined by physicists like Niels Bohr and Albert Einstein. However, at the time of its introduction, Planck himself was hesitant to embrace the full implications of his discovery. He saw his theory primarily as a mathematical tool to explain the empirical data, rather than as a fundamental shift in our understanding of nature. Planck's theory was a small step away from classical physics, but he did not fully realize that it would soon lay the foundation for a radically new branch of physics. He referred to his quantum hypothesis as a mere trick to reconcile theory with observation. Nevertheless, his work sparked a revolution in the field of physics that would unfold over the next few decades. In the years following Planck's breakthrough, his ideas would inspire other physicists to probe deeper into the nature of light, matter, and energy. Planck's discovery of energy quantization created the foundation for what would become the field of quantum mechanics. It prompted further inquiries into the behavior of atoms and subatomic particles, and eventually led to the development of new theories that could explain phenomena that classical physics had failed to account for. One of the first major applications of Planck's quantum theory was in explaining the photoelectric effect, a phenomenon that had confounded scientists for years. In 1905, Albert Einstein used Planck's ideas to explain how light could eject electrons from a metal surface. According to classical wave theory, light of any frequency should be able to eject electrons from a metal if the intensity was sufficiently high. However, experiments showed that light could only eject electrons if it had a frequency above a certain threshold, regardless of the intensity. Einstein proposed that light was not just a wave, but also consisted of discrete packets of energy, or photons. When light strikes a metal surface, these photons collide with electrons, transferring their energy to the electrons and ejecting them from the surface. This explained why light below a certain frequency could not eject electrons even if the intensity was high. Einstein's work on the photoelectric effect, which was based on Planck's theory of quantized energy, earned him the Nobel Prize in Physics in 1921. The concept of quanta, introduced by Planck, also had profound implications for the behavior of atoms. Prior to Planck's work, the prevailing atomic theory was based on the idea that atoms were composed of a dense nucleus surrounded by orbiting electrons. The classical understanding of atomic structure, however, could not explain why atoms emitted light at specific wavelengths. The phenomenon of atomic spectra, where atoms emit light in discrete lines, was a mystery that needed to be solved. In 1913, Niels Bohr, building on Planck's quantization principle, proposed a new model of the atom in which electrons orbit the nucleus in discrete energy levels, or shells. According to Bohr's model, electrons could only occupy certain orbits, and they could absorb or emit energy only when they transitioned between these orbits. This explained the discrete spectral lines observed in atomic emission spectra, such as the famous hydrogen spectrum. Bohr's atomic model was a significant leap forward in understanding atomic structure, but it also highlighted the need for a deeper understanding of the nature of particles and waves. It became increasingly clear that classical physics was inadequate when it came to describing the behavior of particles on the atomic and subatomic scale. The discovery of quantum mechanics was now on the horizon, and Planck's early work on energy quantization was the key that unlocked this new era in physics. At the time, few could predict the profound implications that Planck's work would have on the future of physics. What began as a mathematical solution to a specific problem in black-body radiation soon evolved into a new paradigm that would revolutionize our understanding of the universe at its most fundamental level. The discovery of quantum physics would lead to breakthroughs in atomic theory, the development of new technologies, and a radically new way of thinking about the nature of reality itself. In conclusion, the birth of quantum physics began with Planck's solution to the problem of black-body radiation. By proposing the quantization of energy, Planck laid the groundwork for a new understanding of the physical world. His work prompted further investigations into the nature of light, energy, and matter, eventually leading to the development of quantum mechanics. Planck's theory was a pivotal moment in the history of science, marking the beginning of a scientific revolution that would reshape our understanding of the universe. The groundbreaking work of Max Planck in 1900, which introduced the idea of quantized energy, was just the first step in a long journey that would ultimately lead to the establishment of quantum mechanics. While Planck's quantum hypothesis provided a solution to the problem of black-body radiation, It was not immediately recognized as a revolutionary shift in the fundamental understanding of physics. The implications of quantization, though, would soon expand far beyond the specific issue of blackbody radiation and would be integral in explaining other phenomena that classical physics could not explain. Max Planck's work on the quantization of energy laid the foundation for future development, particularly in the study of the photoelectric effect and atomic structure. His ideas created an entirely new perspective on energy, one where energy is not continuous but instead exists in discrete packets. The implications of this discovery would soon spread to other areas of physics, leading to breakthroughs in understanding the behavior of light, matter, and the very fabric of the universe. The next significant leap in the development of quantum theory came in 1905, when Albert Einstein published his work on the photoelectric effect. Though his work on the photoelectric effect built on Planck's ideas, it was an entirely new concept that extended the notion of quantization to light itself. Einstein's theory of the photoelectric effect showed that light behaves not only as a wave, but also as a stream of particles, which he termed photons. This marked the beginning of the dual nature of light, which would later become a key feature of quantum theory. Einstein's explanation of the photoelectric effect was based on the idea that light consists of discrete quanta, photons, that interact with electrons. When light shines on a metal surface, the photons collide with electrons, transferring their energy to eject the electrons from the surface. Einstein's proposal provided a solution to a problem that had baffled scientists for decades. Why light of lower intensity could still eject electrons if its frequency was high enough. This was contradictory to the classical wave theory, which had predicted that light intensity alone should determine whether electrons would be ejected, irrespective of the frequency. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921. His theory helped solidify the concept of quantization and proved that light, traditionally seen as a continuous wave, also had particle-like properties. This discovery marked the birth of the field of quantum mechanics, and Einstein's work was integral to the understanding of energy and light as discrete packets. The early 20th century saw other key developments that would shape the future of quantum mechanics. In 1913, Niels Bohr built upon Planck's and Einstein's ideas to develop a new model of the atom. Classical models of the atom could not explain the discrete spectral lines that atoms emitted when they were energized. Bohr proposed that electrons in atoms could only occupy specific, quantized energy levels or shells. When electrons moved between these levels, they absorbed or emitted energy in discrete amounts, corresponding to the difference in energy between the levels. This explained the specific spectral lines observed in atomic emission spectra, such as those seen in hydrogen. Bohr's model of the atom, though revolutionary, was still incomplete. It was unable to fully explain the behavior of more complex atoms, and it was eventually superseded by a more comprehensive model of atomic structure. Nevertheless, Bohr's work was instrumental in advancing the concept of quantized energy levels and helping to establish the foundations of quantum mechanics, while Planck, Einstein, and Bohr were laying the groundwork for quantum theory. The field continued to evolve through the contributions of other physicists. In the mid-1920s, Werner Heisenberg, Niels Bohr, and Erwin Schrödinger made key advances that further expanded the principles of quantum mechanics. One of the most revolutionary of these developments came from Heisenberg, who introduced his uncertainty principle in 1927. Heisenberg's uncertainty principle stated that it is impossible to simultaneously measure both the position and momentum of a particle with absolute precision. This was a profound shift from classical mechanics, where it was assumed that both position and momentum could be measured with unlimited accuracy. Heisenberg's principle suggested that, at the quantum level, uncertainty was inherent to the behavior of particles. This concept would become one of the cornerstones of quantum theory, showing that the very act of measurement could influence the system being measured. Heisenberg's uncertainty principle was a direct challenge to the deterministic worldview of classical physics, which had been based on the idea that the universe operated according to fixed laws that could predict future events with certainty. The uncertainty principle introduced a new way of thinking about reality, one in which particles exist in states of probability rather than in deterministic, predictable paths. It was this idea of probability that would come to define quantum mechanics. In parallel with Heisenberg's work, Erwin Schrödinger developed his wave equation in 1926, which described the behavior of particles in terms of waves. Schrödinger's equation was a mathematical description of how particles like electrons could exist in superposition simultaneously in multiple states until measured. This was a radical departure from classical physics, which treated particles as having well-defined positions and velocities at all times. Schrödinger's equation and the wave function that it produced provided a new way of calculating the probabilities of finding particles in particular states. This probabilistic nature of quantum mechanics was to become one of its most significant features. Schrödinger's wave mechanics was closely tied to the growing understanding of wave-particle duality, the idea that particles such as light and electrons could exhibit both wave-like and particle-like behaviors. This duality had first been hinted at by Einstein's work on the photoelectric effect and was further explored by Schrödinger and others in the years that followed. The wave-particle duality of light and matter would become one of the central themes of quantum mechanics and would ultimately lead to the development of quantum field theory, quantum electrodynamics. The 1920s and 1930s saw a rapid accumulation of ideas that formed the basis of quantum mechanics. The principles of superposition, wave-particle duality, and uncertainty challenged the traditional deterministic worldview of classical physics. These new concepts were difficult to reconcile with everyday experience, and many physicists, including Albert Einstein, were uncomfortable with the implications of quantum mechanics, especially the idea that reality was inherently probabilistic. Despite the philosophical debates, quantum mechanics proved to be incredibly successful in explaining the behavior of particles at the atomic and subatomic levels. The theory provided explanations for a wide range of phenomena, including the structure of atoms, the behavior of light, and the nature of chemical bonds. It also paved the way for the development of technologies that have had a profound impact on modern life, such as semiconductors, lasers, and medical imaging devices. In the decades following the development of quantum mechanics, the theory was refined and expanded upon by physicists such as Paul Dirac, Richard Feynman, and others. The development of quantum electrodynamics, QED, in the 1940s and 1950s helped to unify quantum mechanics with the theory of electromagnetism and provided an even more powerful framework for understanding the interactions between light and matter. Today, quantum mechanics remains one of the most successful and influential theories in all of science, and it continues to shape the future of technology, including emerging fields such as quantum computing and quantum cryptography. In conclusion, the discovery of quantum mechanics was not the result of a single breakthrough, but a series of revolutionary ideas that challenged the classical worldview and provided a new framework for understanding the universe. The work of Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger helped to build a theory that explains the behavior of particles at the most fundamental level. Quantum mechanics has reshaped our understanding of the universe and has led to groundbreaking technological advancements. While its counterintuitive principles can be difficult to grasp, quantum mechanics remains one of the most successful and profound scientific theories ever developed. The early 20th century was a time of intense intellectual ferment in the field of physics, as researchers grappled with a series of phenomena that classical physics could not explain. This period was marked by the gradual unraveling of old assumptions about the nature of light, energy, and matter. Among the most significant breakthroughs during this time were the works of Max Planck and Albert Einstein, which laid the foundation for what would become quantum mechanics. The discovery that energy was quantized, proposed by Max Planck in 1900, and the explanation of the photoelectric effect by Albert Einstein in 1905, together formed two keynotes in the development of quantum theory. These discoveries not only revolutionized our understanding of the physical world but also paved the way for an entirely new framework for physics. Max Planck's work began with the problem of blackbody radiation, an issue that had perplexed scientists for years. Classical physics, particularly the laws of thermodynamics, had been successful in explaining a wide range of phenomena, but it failed to account for the spectral distribution of radiation emitted by a perfect blackbody. A blackbody is an idealized object that absorbs all radiation that strikes it and emits radiation based on its temperature. Classical theory predicted that the intensity of radiation would increase indefinitely as the wavelength decreased, which led to the so-called ultraviolet catastrophe, an absurd prediction that energy would increase without bound at short wavelengths. In 1900, Max Planck, a German theoretical physicist, found a solution to this problem that would mark the birth of quantum theory. His solution was based on the idea that energy is not emitted or absorbed continuously, as classical physics assumed, but rather in discrete quantities. These quantities, or quanta, were related to the frequency of the radiation. Planck's hypothesis, though radical at the time, successfully explained the blackbody radiation curve and resolved the ultraviolet catastrophe. Planck introduced a fundamental constant now known as Planck's constant, which linked the energy of a quantum of radiation to the frequency of the electromagnetic wave. His formula for blackbody radiation, known as Planck's law, would soon become a cornerstone of quantum mechanics. The central idea of Planck's theory was that energy is quantized, meaning that it can only exist in specific, discrete amounts. This idea was revolutionary, as it contradicted the classical view that energy was continuous and could be divided into any number of smaller parts. Planck's concept of quantization was the first step toward a new understanding of the physical world, one that would eventually lead to the development of quantum mechanics. Planck himself, however, did not initially fully appreciate the implications of his discovery. He saw his quantization hypothesis as a mathematical device to explain the empirical data rather than a fundamental shift in our understanding of nature. Nevertheless, Planck's work had profound implications. It challenged the traditional view of energy and light, and it would later serve as the foundation for the development of new theories about the behavior of light, matter, and atomic structure. The introduction of quantization raised fundamental questions about the nature of reality, and it laid the groundwork for a series of discoveries that would forever change the course of physics. While Planck's work solved the problem of blackbody radiation, it also opened the door to new questions. One of the most important puzzles was the nature of light itself. Classical physics, particularly the wave theory of light developed by Thomas Young and Augustin Jean Fresnel, treated light as a continuous wave, capable of bending, interfering, and refracting in predictable patterns. This wave theory was successful in explaining many aspects of light's behavior, but it could not account for phenomena like the photoelectric effect. The photoelectric effect refers to the phenomenon in which light shining on a metal surface can cause the emission of electrons from that surface. Classical wave theory predicted that light of any frequency would be able to eject electrons provided the intensity was high enough. However, experiments showed that only light above a certain frequency was able to cause the ejection of electrons, regardless of the intensity. This posed a significant problem for the wave theory of light, and it remained unresolved until Albert Einstein, in 1905, extended Planck's ideas to explain the phenomenon. Einstein proposed that light, which had previously been understood as a wave, could also behave as a particle. He suggested that light consists of discrete packets of energy, which he called quanta or photons. When light strikes a metal surface, these photons collide with electrons, transferring their energy to the electrons and ejecting them from the surface. The energy of each photon was proportional to its frequency, with higher frequency light having more energy. This explanation of the photoelectric effect was based on the idea of energy quantization, which had been introduced by Planck, and it was a direct consequence of the notion that energy is not continuous but discrete. Einstein's explanation of the photoelectric effect was groundbreaking because it introduced the idea of wave-particle duality, the concept that light, and by extension all forms of electromagnetic radiation, can behave both as a wave and as a particle. This was a radical departure from classical physics, where particles and waves were considered distinct entities with separate behaviors. Einstein's work on the photoelectric effect provided compelling evidence for the quantization of energy, and it showed that light cannot be fully described by classical wave theory alone. Einstein's work on the photoelectric effect had far-reaching implications. It not only confirmed the concept of quantization that Planck had introduced, but also demonstrated that the behavior of light could not be explained by classical physics alone. The dual nature of light, as both a wave and a particle, would become one of the central principles of quantum mechanics. Einstein's explanation of the photoelectric effect earned him the Nobel Prize in Physics in 1921, and his work laid the foundation for the development of quantum theory. The discovery of wave-particle duality and the concept of quantization set the stage for the next major step in the development of quantum mechanics, the understanding of atomic structure. In the early 20th century, the structure of the atom was still largely a mystery. The prevailing model, based on the ideas of J.J. Thomson, treated the atom as a uniformly charged sphere with electrons embedded within it, much like plums in a pudding. This plum pudding model could not explain the discrete spectral lines that were observed when atoms were excited. These spectral lines suggested that the behavior of atoms was governed by rules that classical physics could not account for. In 1913, Niels Bohr introduced a new model of the atom that incorporated Planck's and Einstein's ideas. Bohr proposed that electrons in an atom occupy specific, quantized energy levels, or shells around the nucleus. Electrons could absorb or emit energy only by transitioning between these energy levels, and the energy emitted or absorbed during these transitions corresponded to the difference in energy between the levels. Bohr's model successfully explained the discrete spectral lines of hydrogen, which had been a major puzzle for scientists. Bohr's model of the atom was a significant breakthrough in atomic theory, and it marked the beginning of a new era in physics. Bohr's ideas laid the foundation for later developments in quantum mechanics. They also helped establish the concept of quantized energy levels in atoms. However, Bohr's model had its limitations, particularly in explaining the behavior of more complex atoms. Nonetheless, Bohr's work was instrumental in advancing the concept of quantization and in shaping the development of quantum theory. In the years following Planck's and Einstein's discoveries, the development of quantum mechanics gained momentum. Scientists began to realize that the principles of quantization and wave-particle duality applied not only to light, but to all particles, including electrons, protons, and neutrons. This realization led to the development of the Schrödinger equation, a mathematical formula that describes the behavior of particles as waves of probability. Schrödinger's equation was a key component of wave mechanics, and it provided a powerful framework for understanding the behavior of particles at the quantum level. Meanwhile, the work of Werner Heisenberg on the uncertainty principle further deepened the mystery of quantum mechanics. Heisenberg's uncertainty principle stated that it is impossible to simultaneously measure both the position and momentum of a particle with absolute precision. This was a direct challenge to the classical view of a deterministic universe where all properties of particles could, in principle, be measured with perfect accuracy. The uncertainty principle introduced the idea that the very act of measurement could influence the system being measured, and it highlighted the inherent uncertainty and probabilistic nature of quantum systems. Together, the discoveries of Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and others revolutionized the way we understand the fundamental nature of reality. The concept of quantization, introduced by Planck, and the wave-particle duality of light, proposed by Einstein, were pivotal in the development of quantum mechanics. These ideas not only solved long-standing puzzles in physics, but also opened the door to a new way of thinking about energy, matter, and the universe itself. Quantum mechanics has since become one of the most successful and far-reaching theories in science, with applications in fields ranging from particle physics to quantum computing. The development of quantum mechanics also raised profound philosophical questions about the nature of reality. Quantum mechanics challenged the classical worldview, which had been based on the idea that the universe operates according to deterministic laws. Quantum theory introduced the concept of probability and uncertainty at the fundamental level of reality, suggesting that the behavior of particles could only be described in terms of probabilities rather than certainties. This concept has had far-reaching implications, not only for physics but for our understanding of the nature of existence itself. In conclusion, the discoveries of Max Planck and Albert Einstein, particularly their work on black body radiation and the photoelectric effect, were two keynotes in the development of quantum mechanics. Planck's introduction of quantization and Einstein's explanation of the photoelectric effect set the stage for a revolutionary new understanding of the physical world. These discoveries challenged the classical view of energy and light and laid the foundation for the development of quantum theory. Quantum mechanics has since become one of the most successful and influential theories in all of science, reshaping our understanding of the universe and opening up new frontiers in technology and philosophy. The early 20th century witnessed a profound transformation in our understanding of the physical world, driven by a series of intellectual breakthroughs that challenged centuries-old assumptions about light, energy, and matter. These discoveries marked the birth of quantum mechanics, a field of physics that would revolutionize not just our understanding of the microscopic world, but also the very fabric of reality itself. The first two keynotes in this journey were Max Planck's theory of quanta energy and Albert Einstein's explanation of the photoelectric effect. These two discoveries laid the groundwork for the development of quantum theory, each building upon the other, and together forming the cornerstone upon which the edifice of quantum mechanics was constructed. The problem of blackbody radiation was one of the greatest scientific conundrums of the 19th century. Classical physics, which was based on the principles of thermodynamics and electromagnetism, predicted that a perfect blackbody would emit an infinite amount of radiation at high frequencies, particularly in the ultraviolet region of the spectrum. This prediction, known as the ultraviolet catastrophe, was clearly at odds with experimental observation. In reality, blackbodies did not emit infinite radiation, but instead followed a well-defined spectrum that peaked at a certain frequency and then declined at higher frequencies. The inability of classical physics to explain this behavior posed a serious challenge to the scientific community. In 1900, Max Planck, a German theoretical physicist, proposed a solution that would forever alter the course of physics. Planck introduced the concept of quantization, which suggested that energy could not be emitted or absorbed continuously, as classical theory had assumed, but instead in discrete packets. These packets of energy, or quanta, were related to the frequency of the radiation. The idea that energy was quantized was a radical departure from the classical view and marked the beginning of quantum theory. Planck's work on blackbody radiation was based on the assumption that the energy of electromagnetic radiation was quantized, meaning that it could only exist in specific, discrete values. Planck's equation, known as Planck's law, successfully explained the observed spectrum of blackbody radiation by introducing a fundamental constant, now known as Planck's constant, denoted by h. The equation showed that the energy of each quantum of radiation was proportional to its frequency, with the proportionality constant being Planck's constant. This was a groundbreaking discovery because it not only solved the problem of blackbody radiation but also introduced the idea that energy, in its most fundamental form, was not continuous but rather discrete. The concept of quantized energy was a revolutionary idea because it contradicted the classical view, which assumed that energy could be divided into infinitely small amounts. Planck's idea of quantization, although initially a mathematical tool to explain a specific problem, would eventually become the foundation for a new way of thinking about the universe. However, Planck himself did not fully appreciate the implications of his work. He saw his theory as a temporary fix to the problem of blackbody radiation rather than a fundamental shift in our understanding of the physical world. Despite Planck's reservations, his work on quantization had far-reaching consequences. It provided a new way of thinking about energy and light, and it laid the groundwork for future discoveries in quantum mechanics. The idea that energy could only be emitted or absorbed in discrete quantities challenged the traditional view of a deterministic, continuous universe and opened the door to a new way of understanding the behavior of matter and energy at the smallest scales. The next major breakthrough came in 1905 when Albert Einstein extended Planck's idea of quantization to explain the photoelectric effect, a phenomenon that had puzzled scientists for years. The photoelectric effect refers to the observation that when light of a certain frequency strikes a metal surface, it can cause the emission of electrons from that surface. Classical wave theory had predicted that light of any frequency should be able to eject electrons provided the intensity was high enough. However, experiments showed that only light of a frequency above a certain threshold was able to cause the emission of electrons, regardless of the intensity. Einstein proposed that light was not just a wave, as was previously believed, but also consisted of discrete particles of energy, which he called photons. He explained that when light strikes a metal surface, these photons interact with the electrons in the metal, transferring their energy to the electrons. If the energy of the photons is above a certain threshold, the electrons are ejected from the metal. Einstein's explanation was based on Planck's concept of quantized energy and provided a solution to the mystery of the photoelectric effect. His work showed that light, like energy, could be quantized, and it introduced the idea of wave-particle duality, where light exhibits both wave-like and particle-like properties. Einstein's explanation of the photoelectric effect was a major breakthrough in the development of quantum theory because it demonstrated that light, which had traditionally been understood as a wave, also behaved as a particle. This idea of wave-particle duality would become one of the central tenets of quantum mechanics. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921, and it confirmed the validity of Planck's theory of quantization. His work not only provided a solution to a long-standing problem, but also introduced a new way of thinking about light and energy. The implications of Einstein's work were far-reaching. His explanation of the photoelectric effect was based on the principle of quantization, which had been introduced by Planck. Einstein's work demonstrated that the behavior of light could not be fully explained by classical wave theory alone. The idea of light as both a wave and a particle was a radical departure from classical physics and marked the beginning of a new era in the understanding of energy and matter. Einstein's work also provided a new way of thinking about the interaction between light and matter. His photon hypothesis showed that light was not just an electromagnetic wave as had been previously assumed, but a stream of discrete particles that could interact with electrons in a quantized manner. This understanding of light as both a wave and a particle was later incorporated into the development of quantum mechanics, a field that would eventually unify the wave and particle descriptions of nature. At this point, the foundations for quantum mechanics were being laid, but many questions remained unanswered. One of the key puzzles was the nature of atomic structure. The atomic model that was prevalent in the early 20th century, known as the plum pudding model, suggested that atoms were made up of a uniform distribution of positive charge with electrons embedded within it. However, this model could not explain the discrete spectral lines that were observed when atoms were excited. These spectral lines suggested that atoms emitted radiation at specific wavelengths, but classical physics could not explain why this was the case. In 1913, Niels Bohr, building on Planck's and Einstein's work, proposed a new model of the atom. Bohr's model suggested that electrons in atoms occupied specific quantized energy levels, or shells, around the nucleus. According to Bohr, electrons could absorb or emit energy only when they transitioned between these discrete energy levels, and the energy of the radiation emitted or absorbed during these transitions was equal to the difference in energy between the levels. Bohr's model successfully explained the spectral lines of hydrogen and was a significant step forward in our understanding of atomic structure. Bohr's model of the atom was revolutionary because it introduced the idea that the energy levels of electrons were quantized. This was consistent with Planck's and Einstein's work on energy quantization and provided a framework for understanding atomic spectra. However, Bohr's model had its limitations, particularly in explaining the behavior of more complex atoms. Despite its limitations, Bohr's model was an important step in the development of quantum theory and helped to establish the concept of quantized energy levels in atoms. At the same time, the uncertainty principle, developed by Werner Heisenberg in 1927, would further challenge our understanding of the quantum world. Heisenberg's uncertainty principle stated that it is impossible to simultaneously measure both the position and momentum of a particle with absolute precision. This was a direct challenge to the classical view of a deterministic universe, where all properties of particles could be measured with perfect accuracy. Heisenberg's principle introduced the idea that the act of measurement itself could affect the system being measured, and it highlighted the inherent uncertainty in the quantum world. This was a crucial insight that would shape the development of quantum mechanics. In parallel with Heisenberg's work, Erwin Schrödinger formulated his wave equation, which described the behavior of particles as waves of probability. Schrödinger's equation represented a further departure from classical physics, where particles were thought to have well-defined positions and velocities. Instead, Schrödinger's equation suggested that particles existed in a state of probability with different probabilities of being found in different locations. This probabilistic view of the quantum world was one of the key features of quantum mechanics. In conclusion, the discoveries of Max Planck and Albert Einstein were instrumental in the development of quantum mechanics. Planck's introduction of quantization and Einstein's explanation of the photoelectric effect challenged the classical worldview and laid the foundation for a new understanding of energy, light, and matter. These discoveries, along with the later work of Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, led to the development of quantum mechanics, a theory that continues to shape our understanding of the universe today. Quantum mechanics has had far-reaching implications for fields ranging from particle physics to computing, and it remains one of the most successful and profound theories in all of science. The development of quantum mechanics in the early 20th century represents one of the most profound revolutions in the history of science. This transformative journey began with the discovery of quantized energy by Max Planck, which laid the foundation for future developments. From there, the ideas of Albert Einstein regarding the photoelectric effect, which explained the behavior of light and energy, pushed forward our understanding of the quantum world. Later, as physicists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger refined the concepts of energy, quantization, atomic structure, and wave-particle duality, the birth of quantum mechanics became inevitable. The first key breakthrough in the creation of quantum mechanics was Max Planck's introduction of the idea of quantization of energy in 1900. Planck was attempting to resolve the problem of blackbody radiation, a phenomenon that had long troubled scientists. A blackbody, in its ideal form, absorbs all radiation that strikes it and emits radiation based on its temperature. However, classical physics could not explain the observed radiation emitted by blackbodies. Classical theory predicted that the radiation emitted by blackbodies would increase infinitely at short wavelengths, a result known as the ultraviolet catastrophe. This paradox made it clear that something fundamental about our understanding of radiation was wrong. Planck's solution to this problem was revolutionary. He proposed that energy could not be emitted or absorbed continuously, as classical physics had assumed, but rather in discrete packets. These packets of energy, which he called quanta, were proportional to the frequency of the radiation. In other words, energy was quantized, existing in specific, indivisible units. This was a radical departure from classical physics, which had treated energy as continuous. Planck's work successfully explained the spectrum of radiation emitted by a black body, resolving the ultraviolet catastrophe. Although Planck himself viewed his hypothesis as a mathematical trick to solve the specific problem of blackbody radiation, it would later become the cornerstone of the quantum revolution. The introduction of quantization by Planck set the stage for subsequent developments. Albert Einstein's work on the photoelectric effect in 1905 extended Planck's ideas and helped cement the concept of quantized energy in the broader context of light. The photoelectric effect refers to the phenomenon where light shining on a metal surface causes the emission of electrons from that surface. Classical wave theory had predicted that light of any frequency should cause electron ejection provided its intensity was high enough. However, experiments showed that only light of a certain frequency could cause electrons to be ejected regardless of the intensity. This discrepancy posed a serious challenge to the classical view of light as a continuous wave. Einstein's explanation of the photoelectric effect was groundbreaking because it introduced the idea that light, like energy, was quantized. He proposed that light consisted of discrete packets of energy or photons. Each photon carried an amount of energy proportional to its frequency. When light struck a metal surface, these photons collided with electrons and transferred their energy, causing the electrons to be ejected from the surface. This explanation was consistent with Planck's concept of quantization and marked the beginning of the wave-particle duality of light, which would later become one of the central ideas of quantum mechanics. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921. It was one of the most significant developments in physics, as it provided concrete evidence for the quantization of energy and showed that light, which had traditionally been understood as a wave, could also exhibit particle-like properties. This dual nature of light, both wave and particle, was a key feature of quantum mechanics and set the stage for further developments in the theory. Following Einstein's work, Niels Bohr, in 1913, proposed a new model of the atom that incorporated the idea of quantized energy levels. Prior to Bohr's work, the atomic model was based on the ideas of J.J. Thomson and Ernest Rutherford, which envisioned atoms as having a central nucleus with electrons orbiting around it. However, this classical model could not explain the discrete spectral lines that were observed when atoms were excited. These spectral lines indicated that the emission of light from atoms was not continuous, but rather occurred at specific wavelengths. Bohr's model introduced the idea that electrons in an atom could only occupy certain discrete energy levels or shells around the nucleus. Electrons could absorb or emit energy only when they transitioned between these levels. The energy emitted or absorbed during these transitions corresponded to the difference in energy between the levels, which explained the discrete spectral lines observed in atomic emission spectra. Bohr's model successfully explained the spectral lines of hydrogen and marked the first step toward understanding the quantum behavior of atoms. Bohr's model was groundbreaking because it incorporated the ideas of quantization that had been introduced by Planck and extended by Einstein. However, it was limited in its ability to explain the behavior of more complex atoms. Despite its limitations, Bohr's model was instrumental in advancing the understanding of atomic structure and laid the groundwork for the development of quantum theory. At the same time, other physicists, such as Werner Heisenberg and Erwin Schrödinger, were developing new ideas that would further refine the principles of quantum mechanics. In 1925, Heisenberg introduced his uncertainty principle, which stated that it is impossible to simultaneously measure both the position and momentum of a particle with absolute precision. This was a direct challenge to the classical idea of determinism, where the position and momentum of a particle could be known with perfect accuracy. Heisenberg's uncertainty principle suggested that at the quantum level, there was an inherent uncertainty in the behavior of particles. The act of measuring a particle's position, for example, would disturb its momentum, and vice versa. This idea challenged the classical view of a deterministic universe and introduced the concept that, at the quantum level, uncertainty and probability were fundamental aspects of reality. Heisenberg's uncertainty principle was a radical departure from classical physics. Classical mechanics assumed that, in principle, the exact state of a system could be known at any given time, and that the future behavior of the system could be predicted with certainty. In contrast, the uncertainty principle introduced the idea that certain properties of particles, such as position and momentum, were fundamentally indeterminate. This concept of inherent uncertainty became a defining feature of quantum mechanics and had profound philosophical implications. It suggested that the universe at the quantum level was not deterministic, but probabilistic. In parallel with Heisenberg's work, Schrödinger developed his wave equation in 1926, which provided a mathematical framework for describing the behavior of particles in quantum mechanics. Schrödinger's equation was based on the idea that particles, such as electrons, could not be described as point-like objects with definite positions and velocities as they were in classical physics. Instead, Schrödinger proposed that particles behaved like waves, with a wave function that described the probability of finding a particle in a particular location at a given time. Schrödinger's wave equation was a key component of wave mechanics, and it provided a powerful tool for predicting the behavior of quantum systems. The wave function described by Schrödinger's equation did not provide a definite position or velocity for a particle, but instead gave a probability distribution for where the particle might be found. This probabilistic nature of quantum mechanics was in stark contrast to the deterministic nature of classical physics. Schrödinger's equation was able to explain phenomena such as electron diffraction and interference patterns, which could not be explained by classical physics. The wave nature of particles, as described by Schrödinger, became one of the central concepts of quantum mechanics and helped to unify the particle and wave descriptions of nature. The development of quantum mechanics continued to progress in the following decades, with physicists such as Paul Dirac, Richard Feynman, and others refining the theory and applying it to new problems. One of the most significant developments in quantum mechanics was the development of quantum electrodynamics (QED). which provided a unified framework for understanding the interaction between light and matter. QED, developed by Dirac, Feynman, and others, combined quantum mechanics with the theory of electromagnetism and explained the behavior of particles and electromagnetic fields in a consistent way. QED has been one of the most successful theories in physics, accurately predicting a wide range of phenomena, from the behavior of electrons in atoms to the interaction of light with matter. Today, quantum mechanics remains one of the most successful and far-reaching theories in science. It has provided explanations for a wide range of phenomena, from the behavior of atoms and molecules to the interactions between particles at the subatomic level. Quantum mechanics has had a profound impact on fields ranging from particle physics and chemistry to information technology and computing. The development of quantum computers, for example, is based on the principles of quantum mechanics and promises to revolutionize computing power in the coming years. Despite its success, however, quantum mechanics continues to challenge our understanding of the nature of reality, the probabilistic nature of the quantum world, as well as the concept of wave-particle duality, forces us to reconsider our classical intuitions about the nature of matter and energy. In conclusion, the development of quantum mechanics was driven by a series of groundbreaking discoveries, beginning with Max Planck's introduction of quantized energy and Albert Einstein's explanation of the photoelectric effect. These discoveries, along with the work of Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, helped to create a new framework for understanding the behavior of matter and energy at the smallest scales. Quantum mechanics has since become one of the most successful and influential theories in science, reshaping our understanding of the universe and opening up new frontiers in technology and philosophy. The early 20th century marked a period of immense transformation in the field of physics, driven by a series of discoveries that challenged classical theories and paved the way for the birth of quantum mechanics. The advent of quantum theory, a revolution that would fundamentally alter our understanding of the physical world, can be traced back to the work of several key figures whose groundbreaking ideas provided answers to problems that classical physics could not explain. In particular, the introduction of quantization by Max Planck, followed by Albert Einstein's work on the photoelectric effect, and the later development in atomic theory by Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, were pivotal milestones in the creation of quantum mechanics. In the late 19th century, one of the most perplexing problems that scientists faced was related to blackbody radiation, the electromagnetic radiation emitted by an idealized object known as a blackbody, an object that absorbs all radiation incident upon it. Classical physics, specifically the laws of thermodynamics and electromagnetism, had provided accurate predictions for a wide range of phenomena but failed to explain the observed pattern of radiation emitted by blackbodies. According to classical theory, the radiation intensity emitted by a blackbody would increase infinitely as the wavelength of radiation decreased, a prediction that led to the so-called ultraviolet catastrophe. This prediction was absurd because it suggested that objects would radiate infinite energy at short wavelengths, a result that was in stark contrast to experimental observation. In 1900, Max Planck, a German physicist, was tasked with resolving this problem. Planck's work led to the first major breakthrough in the quantum revolution. Instead of relying on the continuous nature of radiation as classical physics had, Planck proposed that energy was quantized, meaning that energy could only be absorbed or emitted in discrete units, or quanta, rather than in a continuous flow. This was a radical shift in thinking, as it contradicted the classical belief in the smooth, continuous nature of energy. Planck introduced the concept of Planck's constant, a fundamental constant in physics that relates the energy of a quantum of radiation to its frequency. His work resolved the ultraviolet catastrophe and accurately described the spectrum of blackbody radiation, which was in line with experimental data. Although Planck initially viewed his quantization hypothesis as a mathematical trick to explain a specific phenomenon, the implications of his discovery were far-reaching. His introduction of the quantization of energy laid the foundation for a new understanding of the physical world, one in which energy was not a continuous variable, but instead existed in discrete packets. This idea would become the cornerstone of quantum mechanics and would have profound implications for our understanding of light, matter, and the universe itself. Following Planck's work, Albert Einstein, in 1905, extended the concept of quantization to explain the photoelectric effect, a phenomenon that had confounded scientists for decades. The photoelectric effect refers to the observation that when light shines on a metal surface, it can cause the emission of electrons from that surface. Classical wave theory of light predicted that light of any frequency would be able to eject electrons from a metal surface, provided the intensity of the light was sufficiently high. However, experiments showed that only light above a certain frequency could cause electrons to be ejected, regardless of the light's intensity. This discrepancy posed a serious challenge to the classical understanding of light. Einstein proposed a revolutionary idea to explain this phenomenon. He suggested that light, which had previously been understood as a continuous wave, could also behave as a stream of discrete particles, which he called photons. According to Einstein, when light strikes a metal surface, these photons collide with electrons, transferring their energy to the electrons and ejecting them from the metal surface. The energy of the photon was proportional to the frequency of the light. This provided a clear explanation for why light below a certain frequency could not eject electrons, because the energy of the photons was too low to overcome the binding energy of the electrons in the metal. Einstein's explanation of the photoelectric effect was a breakthrough, because it demonstrated that light, which had been understood as a continuous wave for centuries, also had particle-like properties. His work confirmed Planck's idea of quantization and introduced the concept of wave-particle duality, where light could exhibit both wave-like and particle-like behavior depending on the context. This discovery earned Einstein the Nobel Prize in Physics in 1921 and solidified the concept of quantization as a fundamental principle in physics. Einstein's work also had profound implications for the development of quantum mechanics. His theory of the photoelectric effect provided experimental evidence for the quantization of energy, and it laid the groundwork for future investigations into the nature of light and matter. The idea of wave-particle duality, which Einstein introduced, became one of the central themes of quantum mechanics. It suggested that light and other particles, such as electrons, could exhibit characteristics of both waves and particles, depending on how they were observed. This duality would become a key aspect of quantum theory, which would later be developed into a comprehensive framework for understanding the behavior of particles at the subatomic level. Building on these ideas, Niels Bohr introduced a new model of the atom in 1913 that incorporated the principles of quantization. Before Bohr's work, the atomic model proposed by Ernest Rutherford in 1911, which described atoms as having a small, dense nucleus surrounded by orbiting electrons, could not explain the observed discrete lines in the atomic spectra of elements. When atoms were excited, they emitted light at specific wavelengths, forming a series of distinct lines known as spectral lines. Classical physics could not account for this discrete emission, as it predicted a continuous spectrum of radiation. Bohr's model of the atom, based on the ideas of Planck and Einstein, proposed that electrons in an atom occupied specific, quantized energy levels around the nucleus. Electrons could not exist between these energy levels, they could only occupy distinct orbits or shells. When electrons transitioned between these energy levels, they absorbed or emitted energy in discrete amounts, corresponding to the difference in energy between the levels. This explanation accounted for the discrete spectral lines observed in atomic spectra. Bohr's model successfully explained the spectral lines of hydrogen, the simplest atom, and provided a clear framework for understanding atomic behavior. Bohr's model of the atom was a major step forward in atomic theory. It introduced the idea that atomic energy levels were quantized, which was consistent with Planck's and Einstein's work on the quantization of energy. Bohr's model provided a new perspective on the structure of atoms, but it also had its limitations. It was unable to explain the spectra of atoms more complex than hydrogen, and it was eventually replaced by more advanced theories, such as the quantum mechanical model of the atom. Nonetheless, Bohr's model was instrumental in advancing the understanding of atomic structure and laid the foundation for the development of quantum mechanics. Meanwhile, the development of quantum mechanics continued through the work of other physicists, particularly Werner Heisenberg and Erwin Schrödinger. Heisenberg's uncertainty principle, introduced in 1927, challenged the classical view of determinism. Heisenberg's principle stated that it is impossible to measure both the position and momentum of a particle simultaneously with absolute precision. This was a direct challenge to the classical notion that the behavior of particles could be known with perfect accuracy. The uncertainty principle suggested that, at the quantum level, uncertainty and probability were intrinsic to the nature of particles. This principle would later become one of the cornerstones of quantum mechanics. In the same period, Erwin Schrödinger developed his wave equation, which provided a mathematical description of how particles behave as waves of probability. Schrödinger's equation revolutionized our understanding of quantum systems by describing particles in terms of wave functions, which provide the probability distribution for where a particle might be found. Schrödinger's equation described particles not as point-like objects with definite positions as they were in classical physics, but as probability waves that spread out over space and time. This wave nature of particles was a key feature of quantum mechanics and became one of the central concepts in the theory. Together, the discoveries of Planck, Einstein, Bohr, Heisenberg, and Schrödinger led to the formulation of quantum mechanics, a theory that describes the behavior of particles at the subatomic level. Quantum mechanics introduced new concepts such as quantization, wave-particle duality, and the uncertainty principle, which were completely at odds with the classical worldview. These ideas not only provided a new understanding of the behavior of matter and energy, but also led to groundbreaking advances in technology, from the development of semiconductors and lasers to the emerging field of quantum computing. Quantum mechanics also had profound philosophical implication. The probabilistic nature of quantum mechanics, combined with the wave-particle duality and the uncertainty principle, challenged classical notions of determinism and causality. It suggested that, at the quantum level, the universe is inherently unpredictable and that the act of observation plays a fundamental role in determining the behavior of particles. These ideas have had a lasting impact on our understanding of the nature of reality. They continue to be the subject of debate and exploration in both physics and philosophy. In conclusion, the creation of quantum mechanics was driven by a series of transformative discoveries, beginning with Planck's introduction of quantum energy, followed by Einstein's work on the photoelectric effect, and culminating in the development of atomic theory by Bohr, Heisenberg, and Schrödinger. These breakthroughs fundamentally changed our understanding of the physical world and set the stage for a new era in physics. Quantum mechanics has since become one of the most successful and far-reaching theories in science, with applications in a wide range of fields from particle physics to technology and computing. Despite its counterintuitive nature, quantum mechanics remains one of the most accurate and powerful theories ever developed, and it continues to shape our understanding of the universe. The development of quantum mechanics is one of the most significant milestones in the history of science, with its foundations built on several groundbreaking discoveries. The first major keynote in this revolution came from Max Planck's proposal of energy quantization in 1900, which introduced the idea that energy is not continuous, but is instead emitted or absorbed in discrete units. This concept was revolutionary because it directly challenged the classical view that energy could be arbitrarily divided into smaller parts. Planck's work on blackbody radiation, which explained the spectrum of radiation emitted by a perfect blackbody, resolved a long-standing problem in physics known as the ultraviolet catastrophe. His formula, known as Planck's law, was the beginning of the quantum era, where energy levels could only exist in fixed amounts, laying the groundwork for the quantum theory that would emerge over the next few decades. Albert Einstein's explanation of the photoelectric effect in 1905 extended Planck's ideas and introduced the concept of wave-particle duality. Einstein proposed that light, typically thought of as a wave, also had particle-like properties. His work showed that light consists of discrete particles called photons, which carry energy that could interact with electrons in metal surfaces, causing their emission. This was a critical breakthrough because it demonstrated that light behaved both as a wave and as a particle, depending on the experiment. The photoelectric effect provided the experimental evidence for quantized energy and was one of the key events that pushed the development of quantum mechanics forward. Einstein's work also led to his Nobel Prize in Physics in 1921, cementing his contribution to the theory. The third keynote in the development of quantum mechanics came with Niels Bohr's model of the atom in 1913. Bohr applied the idea of quantized energy levels to explain atomic structure. Before Bohr, The atom was thought to consist of a central nucleus surrounded by orbiting electrons. But this model failed to explain the discrete spectral lines observed in atomic spectra. Bohr proposed that electrons could only occupy specific, quantized orbits or energy levels around the nucleus, and that they could absorb or emit energy only when they transitioned between these levels. This was a revolutionary idea that successfully explained the spectral line of hydrogen and introduced the concept of quantized energy levels in atoms. Bohr's model of the atom laid the foundation for future developments in quantum theory, even though it had limitations in explaining more complex atoms. The fourth keynote came with the development of Heisenberg's uncertainty principle in 1927, which introduced an entirely new perspective on the nature of measurement in quantum mechanics. Heisenberg stated that it is impossible to precisely measure both the position and momentum of a particle simultaneously. This uncertainty was not due to limitations in measurement devices, but was an intrinsic property of particles at the quantum level. The uncertainty principle directly contradicted classical physics, which assumed that particles could be measured with infinite precision. Heisenberg's principle introduced the concept that at the quantum level there is an inherent limit to how much we can know about a particle's properties. This shifted our understanding of reality, suggesting that the universe operates in a probabilistic rather than deterministic manner at the microscopic scale. The uncertainty principle became one of the foundational pillars of quantum mechanics and radically changed the way scientists approached the study of atomic and subatomic particles. The creation of quantum mechanics was a gradual process driven by a series of pivotal discoveries that challenged classical physics and introduced a new way of understanding the microscopic world. The fifth keynote in the development of quantum theory can be attributed to the formulation of Schrödinger's wave equation in 1926. Schrödinger, building on the work of Heisenberg and others, introduced the idea that particles like electrons could not be treated as classical objects with fixed positions and velocities, but instead should be understood as existing as waves of probability. Schrödinger's equation described how these waves evolved over time and could be used to calculate the probability of finding a particle in a particular location. This equation marked a significant departure from classical physics and laid the foundation for the wave mechanics approach to quantum mechanics. Schrödinger's work provided a more precise mathematical framework for understanding the behavior of particles at the atomic scale, further advancing the concept of wave-particle duality introduced earlier by Einstein and others. The sixth keynote in quantum theory came with the concept of quantum superposition. This idea, central to quantum mechanics, holds that particles can exist in multiple states simultaneously until they are measured or observed. This is most famously demonstrated in Schrödinger's thought experiment known as Schrödinger's cat, where a cat inside a box is both alive and dead until the box is opened, collapsing the superposition into one definite state. Quantum superposition is a phenomenon that has been experimentally confirmed through various experiments, including the double-slit experiment, where particles like electrons or photons behave as both waves and particles depending on the measurement. This concept fundamentally challenges classical physics, where an object could only exist in one state at a time, and introduces a new way of understanding reality, where uncertainty and multiple possibilities are inherent to nature. Another crucial concept introduced during the development of quantum mechanics was quantum entanglement. First discussed by Einstein, Podolsky, and Rosen in the 1930s, entanglement refers to the phenomenon in which two or more particles become linked in such a way that the state of one particle directly influences the state of the other, no matter how far apart they are. This idea was initially met with skepticism because it appeared to violate the principles of locality and causality, central tenets of classical physics. However, later experiments, notably those by physicist John Bell and others, confirmed that entangled particles do indeed exhibit correlations that cannot be explained by classical physics. Quantum entanglement has profound implications for our understanding of space, time, and information, and it forms the basis for emerging technologies like quantum computing and quantum cryptography, where particles are used to store and transmit information in fundamentally secure ways. The eighth keynote of quantum mechanics emerged through the development of quantum field theory, QFT, which combined quantum mechanics with special relativity to describe the fundamental forces of nature. Quantum field theory posits that particles are excitations or quanta of underlying fields that permeate space. The most well-known quantum field theory is quantum electrodynamics, QED, which describes the interaction of light and matter. In QED, light is treated as both a particle, photon, and a wave, and the theory explains how particles interact by exchanging virtual particles. This framework was developed through the work of physicists such as Paul Dirac, Richard Feynman, and Julian Schwinger, and it has been extremely successful in predicting experimental outcomes with remarkable accuracy. The development of QFT revolutionized particle physics, leading to the discovery of the Higgs boson and providing the theoretical foundation for the standard model of particle physics, which describes the fundamental particles and forces that make up the universe. The ninth and final keynote of quantum mechanics involves the concept of quantum computing, which takes advantage of the unique properties of quantum mechanics, such as superposition and entanglement, to perform calculations that are impossible or infeasible for classical computers. Quantum computers use quantum bits, or qubits, which can exist in multiple states simultaneously, unlike classical bits that are either 0 or 1. This allows quantum computers to process vast amounts of data in parallel, making them potentially powerful tools for solving complex problems in areas like cryptography, materials science, and optimization. The development of quantum computing represents the convergence of theoretical physics and practical technology. It promises to revolutionize many fields by solving problems that classical computers cannot handle efficiently. As the field continues to grow, it brings with it new challenges, particularly in the realms of stability, error correction, and scalability. But it also offers the potential for groundbreaking advances in computing power and information processing. The development of quantum mechanics is a monumental achievement in the history of science, with each breakthrough adding a new layer to our understanding of the microscopic world. The sixth keynote in the evolution of quantum theory focuses on the concept of the wave-particle duality of matter. This idea emerged from the realization that particles, such as electrons, exhibited both wave-like and particle-like properties, depending on the nature of the experiment. This duality was first proposed by Louis de Broglie in 1924, who suggested that, just as light exhibits both wave and particle characteristics, particles like electrons also have a wave nature. De Broglie's hypothesis was experimentally confirmed in the same decade through electron diffraction experiment, where electrons were observed to produce interference patterns, a characteristic of waves. The wave-particle duality became a cornerstone of quantum theory, highlighting the complexity and richness of the quantum world. It challenged classical physics, which treated waves and particles as distinct entities, and opened the door to a new understanding where objects could no longer be classified strictly as either waves or particles. The seventh keynote in the development of quantum mechanics is the Heisenberg uncertainty principle, formulated in 1927. Werner Heisenberg's principle states that it is impossible to simultaneously measure both the position and momentum of a particle with absolute precision. The more accurately one of these properties is measured, less accurately the other can be determined. This was a radical departure from classical physics, where it was assumed that all properties of particles could be known with perfect precision. The uncertainty principle introduced the idea that at the quantum level, the universe is fundamentally probabilistic, not deterministic. This principle was not a limitation of experimental tools, but a fundamental property of nature. It challenged our classical intuition and suggested that the act of measurement itself has a profound effect on the system being measured. The uncertainty principle reshaped the way we think about reality, making it clear that the very fabric of the quantum world was governed by uncertainty and probability, rather than certainty and precision. The eighth keynote in quantum mechanics is the concept of quantum superposition, a phenomenon where particles can exist in multiple states at once. Quantum superposition is perhaps most famously illustrated by Schrödinger's cat thought experiment, where a cat inside a sealed box is considered to be both alive and dead at the same time until it is observed. This idea arises from the wave function, a mathematical description of a particle's quantum state, which can represent a combination or superposition of different possible outcomes. Only when an observation or measurement is made does the superposition collapse into one definite state. Quantum superposition is a key feature of quantum mechanics and has been experimentally verified in numerous experiments, such as the double-slit experiment, where particles exhibit interference patterns that suggest they are passing through two slits simultaneously, behaving as waves and particles at the same time. Superposition plays a critical role in quantum computing, where quantum bits, qubits, can exist in multiple states at once, enabling quantum computers to perform complex computations much faster than classical computers. Another important development in quantum theory is quantum entanglement, which was first discussed by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935. Quantum entanglement refers to the phenomenon in which the quantum states of two or more particles become linked in such a way that the state of one particle directly influences the state of another, even if the particles are separated by large distances. This phenomenon seems to defy the classical notion of locality, where objects are only influenced by their immediate surroundings. The idea of entanglement raised profound questions about the nature of reality, suggesting that particles could be connected in a way that transcended space and time. Despite initial skepticism, entanglement was experimentally confirmed in the 1960s by John Bell and others, whose work showed that entangled particles do indeed exhibit correlations that cannot be explained by classical physics. Quantum entanglement is a key component of emerging technologies such as quantum computing and quantum cryptography, where entangled particles are used to perform computations and transmit information in ways that are impossible for classical systems. The 10th keynote in the evolution of quantum mechanics is the development of quantum field theory, QFT, which combines quantum mechanics with special relativity to describe the fundamental forces of nature. Quantum field theory posits that particles are excitations of underlying fields that permeate space. In this framework, the electromagnetic field is quantized, and light is treated as both a particle, photon, and a wave. The most famous example of quantum field theory is quantum electrodynamics, QED, developed by physicists such as Richard Feynman, Julian Schwinger, and Shinichiro Tominaga. QED describes the interaction of light and matter and provides an accurate description of electromagnetic phenomena at the quantum level. The predictions of QED have been tested to incredible precision, and the theory has successfully explained a wide range of phenomena, from the behavior of electrons in atoms to the interaction of photons with matter. Quantum field theory has been instrumental in the development of the Standard Model of Particle Physics, which describes the fundamental particles and forces in the universe, excluding gravity. Finally, the development of quantum mechanics also led to the emergence of quantum computing, which represents one of the most exciting and promising applications of quantum theory. Quantum computers exploit the principles of quantum mechanics, such as superposition and entanglement, to process information in ways that classical computers cannot. Unlike classical bits, which can exist in one of two states, 0 or 1, quantum bits or qubits can exist in multiple states simultaneously, thanks to superposition. This allows quantum computers to perform calculations in parallel, offering exponential speed-up over classical computers for certain types of problems. Quantum computing holds the potential to revolutionize fields such as cryptography, artificial intelligence, and materials science by solving complex problems that are currently intractable for classical computers. However, the development of practical quantum computers is still in its early stages, with significant challenges related to error correction, stability, and scalability remaining to be overcome. In conclusion, quantum mechanics has fundamentally altered our understanding of the universe, introducing concepts such as wave-particle duality, uncertainty, superposition, entanglement, and quantum field theory. These ideas have not only reshaped the field of physics, but have also opened up new avenues for technological innovation, particularly in areas such as quantum computing and quantum cryptography. As our understanding of quantum mechanics continues to evolve, it promises to bring about even more groundbreaking discoveries, further transforming our view of the physical world and the universe at large. The development of quantum mechanics is marked by a series of groundbreaking discoveries that revolutionized the way scientists understood the natural world. One of the keynotes that solidified the foundation of quantum theory is the concept of quantum superposition, introduced in the early 20th century. Quantum superposition refers to the idea that particles, such as electrons, can exist in multiple states simultaneously until they are measured. This concept defies classical intuition, which suggests that objects can only exist in one state at a time. The most famous example of this phenomenon is Schrödinger's cat thought experiment, where a cat inside a box can be both alive and dead at the same time until observed. Superposition is a crucial feature of quantum mechanics and has been experimentally verified in many experiments, such as the double-slit experiment, where particles exhibit interference patterns that suggest they are passing through two slits simultaneously. This behavior challenges our classical understanding and highlights the fundamental differences between the quantum and classical worlds. Another keynote in the development of quantum mechanics is wave-particle duality, a concept that emerged from experiments on light and matter. In the early 20th century, experiments like the photoelectric effect, explained by Albert Einstein, demonstrated that light exhibits both wave-like and particle-like behavior. Einstein proposed that light is composed of discrete packets of energy, or photons, which behave as particles. In certain experiments, such as when they collide with electrons in the photoelectric effect, on the other hand, light also exhibits wave-like characteristics, such as interference and diffraction, which are associated with classical wave theory. This duality, where particles like electrons also behave like waves, became a fundamental principle of quantum mechanics, demonstrating the inability of classical physics to fully explain phenomena at the atomic and subatomic levels. The third keynote in quantum mechanics is Heisenberg's uncertainty principle, formulated in 1927. Werner Heisenberg's principle states that it is impossible to measure both the position and momentum of a particle with absolute precision at the same time. The more accurately one of these properties is measured, the less accurately the other can be known. This is not due to limitations in measurement technology, but reflects a fundamental property of nature. The uncertainty principle implies that, at the quantum level, the universe is governed by probability rather than certainty. This was a radical departure from classical mechanics, which assumed that if we knew the position and momentum of a particle, we could predict its future behavior with complete accuracy. The uncertainty principle has profound implications for our understanding of reality, suggesting that the quantum world is fundamentally indeterminate. The concept of quantum entanglement is another pivotal development in quantum theory. In quantum entanglement, particles that have interacted with each other become linked, such that the state of one particle is directly related to the state of another, even if they are separated by vast distances. This phenomenon, which Albert Einstein famously referred to as spooky action at a distance, was initially met with skepticism because it seemed to violate the principle of locality, which states that objects can only be directly influenced by their immediate surroundings. However, later experiments, particularly those conducted by John Bell and others, confirmed that entangled particles do exhibit correlations that cannot be explained by classical physics. Quantum entanglement has since become a critical concept in emerging technologies such as quantum computing and quantum cryptography, where it is used to perform computations and secure communication channels in ways that classical systems cannot. A major breakthrough in quantum theory came with the development of quantum field theory, QFT, which merges quantum mechanics with special relativity. Quantum field theory posits that the fundamental forces of nature, including electromagnetism and gravity, are mediated by quantum fields. Instead of treating particles as independent entities, QFT views them as excitations or disturbances in these underlying fields. The most well-known application of quantum field theory is quantum electrodynamics, QED, which describes the interaction between light and matter. QED has been incredibly successful in explaining a wide range of phenomena and has accurately predicted the behavior of electrons and photons with great precision. Quantum field theory represents the culmination of decades of work and has provided a comprehensive framework for understanding particle interactions at the most fundamental level. The development of quantum computing represents a practical application of quantum theory that has the potential to revolutionize information processing. Classical computers process data using bits, which can either be in a state of 0 or 1. However, quantum computers use quantum bits or qubits, which can exist in multiple states simultaneously due to the principle of superposition. This allows quantum computers to perform many calculations in parallel, making them potentially much more powerful than classical computers for certain types of complex problems. Quantum computing has the potential to impact fields such as cryptography, material science, and artificial intelligence, but there are still significant challenges to overcome, including issues with quantum coherence, error correction, and scalability. Finally, one of the most profound implications of quantum mechanics is its impact on the philosophy of science and reality. Quantum mechanics has challenged classical notions of determinism, causality, and locality. The probabilistic nature of quantum systems, where outcomes can only be predicted in terms of probabilities rather than certainties, has led to various interpretations of the theory, such as the Copenhagen interpretation, the many worlds interpretation, and the pilot wave theory. These interpretations seek to explain the strange and counterintuitive features of quantum mechanics, such as wave function collapse, and the role of the observer. Quantum mechanics suggests that at the smallest scales, reality is fundamentally different from the everyday world we experience. This has profound implications for our understanding of the nature of existence, the role of observation in determining reality, and the limits of human knowledge. In conclusion, quantum mechanics has fundamentally changed the way we understand the universe, from the behavior of subatomic particles to the very fabric of reality itself. Key developments such as quantum superposition, wave-particle duality, Heisenberg's uncertainty principle, quantum entanglement, quantum field theory, quantum computing, and the philosophical implications of quantum theory have reshaped our understanding of the natural world. These discoveries not only revolutionized physics, but have also opened new frontiers in technology and philosophy, offering new possibilities for the future of science and human knowledge.